Hello everyone, today we are going to talk about the voltage breakdown. First, we will explain dielectric breakdown and show it through a simple experimental video. Second, we will discuss why considering the possibility of dielectric breakdown is crucial in the context of superconducting magnets. The following is an explanation of breakdown voltage. Paschen's law provides an equation that determines the breakdown voltage, which is the starting point for a discharge or electric arc between two electrodes in a gas. This equation is derived as a function of the gas pressure and the gap length between the electrodes. The graph on the left is called the Paschen curve, which uses the formula to calculate the breakdown voltage values. The x-axis represents the product of the gas pressure and the distance between the two electrodes. The y-axis represents the breakdown voltage for that gas. The breakdown voltage can be calculated using the equation shown on the right, considering the following parameters and units. On the left, we have an example of a dielectric breakdown test conducted on a copper plate at Seoul National University of Transportation. This system was completely opened using insulated with fiberglass reinforced plastics, the FRP material, to prevent any direct electrical contact. However, as we can observe from the video, dielectric breakdown occurred about 2 kV range, allowing current to flow along the sides of the insulation material. As shown in the photograph above, this led to significant damage to the magnet. The breakdown compromised the insulation, illustrating the severe consequences of such electrical failures in practical applications. Superconducting magnets are typically characterized by their extremely low resistance, assumed to be negligible in this page. Before discussing dielectric breakdown in these magnets, let's consider that the resistance in the system is zero, and the observed voltage at the terminals is also close to zero. However, if a quench occurs in the magnet, creating a normal zone where the material temporarily loses its superconducting properties and exhibits resistance, this changes the scenario significantly. Resistive voltages develop in these normal zones, altering the current flowing through the magnet. While inductive voltage tries to counteract these changes, maintaining zero voltage at the terminals, significant internal voltages can develop within the magnet itself. The following diagram illustrates the relationship between the proportion of the normal zone within the magnet and both inductive and resistive voltages. The solid line represents the resistive voltage generated by the normal zone, the dotted line shows the inductive voltage, and the dashed line indicates the total voltage, which peaks when the normal zone accounts for 50% of the magnet. What is crucial to understand from this page is not only just how the internal voltage scales with the normal zone proportion, but also the fact that during a quench, although terminal voltage might remain at 0 V, substantial internal voltages can occur within the magnet that are not observable at the terminals. And this can lead to dielectric breakdown in superconducting magnet. Breakdown voltage refers to the voltage at which dielectric breakdown occurs, leading to insulation failure. This voltage can be measured using Paschen's voltage test, which assesses the dielectric breakdown of gases. The breakdown voltage varies depending on the type of gas, its pressure, and the distance between the electrodes. In superconducting magnets, the appearance of a sudden normal zone can lead to the calculation of the maximum internal voltage generated within the magnet, depending on the proportion of the normal zone. Typically, insulators have a specific dielectric strength they can withstand. However, in superconducting magnets, particularly large voltages can be induced internally, which are not detectable at the terminals. These hidden voltages pose a significant risk as they can far exceed the designed insulation strength of the components, potentially leading to catastrophic insulation failures.